welcome guests and members, and welcome to the main meeting of the Ottawa Centre of the Royal Astronomical Society of Canada. I'd like to start by wishing all those of you in the crowd who are Star Wars fans a happy Star Wars Day, and may the 4th be with you.
Yes.
So we've got a great program tonight. We're going to have Dave Chisholm give us his usual talk on the Ottawa skies. Brian McCullough is going to give us a brief tour of the moon. Chuck O'Dale is going to give us a talk on bolides. And then after the break, we have a very special speaker, Dr. Robin Fiore, giving us a talk on the dark side of the auroras. Dave Lazon is here to give us an update on the FLO. We'll have observations and the observing challenge, and then various announcements. These are our new members from last month: Brenda Cote, David Goretsky, Andre Tene-Sens. Let's give them a warm welcome. As you may recall, we had International Astronomy Day last month on April 21st. We held an event here at the museum. We had daytime solar observing for the public. And in the evening, we set up just behind the hangar building here for a nighttime star party. So I'd like to thank all the organizers and volunteers of that event that helped make it a success. Thank you. Okay, Dave, take it away. Just back forward.
Okay, super. Okay, let's take a look at what's happening in the month of May. The full moon is going to be on May the 29th. We do have a meteor shower, May 6th and 7th. And this is the Eta Aquarids, and it's about 30 meteors per hour. And it's produced by dust particles left behind by Comet Halley. The shower runs annually from April 19th to May 28th and peaks on the 6th over to the 7th. The waning gibbous moon will block most of the fainter meteors, of course, but you should be able to catch a few good ones if you're patient after midnight. Okay, let's just take a look quickly through the planets here. Mercury is not visible. Venus is visible all month just after sunset. Mars is visible in the early morning. Jupiter is finally rising at a reasonable time, so 8:40 tonight, and then towards the end of the month it's rising at 6:23. And it's at opposition closest to the Earth on May the 9th. It'll be a little bit low on the horizon, but that would be a good time to try to capture some pictures. Saturn is visible in the late evening, early morning all month. Uranus is visible in the early morning. Neptune is visible in the early morning as well. The International Space Station. What I'm going to do is I'm going to tell you folks how to find out when it's going to be up there. The problem I have is that I often work on my presentations quite a ways in advance. For right now, I've just finished the October presentation. Unfortunately, the calculations for the International Space Station are only valid 10 days in advance. So if I put in the times for October, I'm going to be way out. So I'm going to show you folks how to do it yourself. And so the website that I use is heavensabove.com. That's a great website. And the times and dates are valid for approximately 10 days. When you get into that site, first thing you've got to do is make sure that you're in Ottawa. Otherwise, you're off the coast of Africa at the equator, and all your times will be wrong. Voice of experience. Then there's a satellite section on the page. You go there, you click on the ISS, and it's going to come up with a list of the passes. Now, I did this slide presentation, worked on it in February, so this sort of gives you an idea of what you see. So the first column is the magnitude. So the more negative, the better. So the 1st of March looks like a great time, but then you take a look at it, and the highest point on the 1st of March is 57 degrees, so it's not as high in the sky. If you click on a particular event, it then gives you all the details. when it exits the shadow, maximum altitude when it drops below 10 degrees and when it sets. So I encourage you to go up there and take a look at it. And as I said, it's valid for 10 days from the time that you look at that. And there's our cartoon of the month. Thank you very much.
All right, thanks, Dave. Okay, up next we've got Brian McCullough. He's going to be sharing some beautiful imagery from the Lunar Reconnaissance Orbiter. Oh, well, you can just hit next.
Where's the next one?
Hit that button, it'll start playing.
Okay. Well, good evening, everybody. What was the reference? It was May what?
May the 4th.
May the 4th.
Luke, I am your presenter. It's my little nightlight for the observatory. Anyway, Lunar Reconnaissance Orbiter. I found this, there was a video that was going around on the internet, and I don't know if everybody saw it, so I thought I'd share it with you. The LRO, Lunar Reconnaissance Orbiter, a very small spacecraft that was launched in 2009, December 2009. It spent 4.5 days getting out to the moon, and went into an orbit around the moon. Initially it was a fairly low circular orbit that was about half the altitude of the Apollo spacecraft when they were waiting for the lunar landers to come back. And was doing imaging. So what's happened is the American administration has decided that they will go to the moon, back to the moon, before they do any attempt on Mars. So what they're doing with LRO is doing mapping of the surface of the moon in great detail. Sometimes they're getting down to 0.5 meter resolution, and they're looking at the mineralogical composition of it. They're putting information together from the Grail spacecraft, looking at the mass concentrations in the moon. So basically they're looking all over the moon for, in good detail, for other places where they could put astronauts. You'll see some of that in the video. Apparently the video is in stunning 4K resolution. I have no idea what that means, but I think it's pretty good resolution is what it is. All right, so I think we'll roll the video here, and I'll click it, and away we go here.
The Moon. It's our nearest neighbor in space, and data we gather from its features can tell us a lot about the rest of our solar system. And through the eyes of the LRO spacecraft, we can explore the lunar surface in all new ways, in fascinating detail. Our tour begins on the western border, where the near side of the moon meets the far side. The enormous feature is a lunar crater, and it's known as the Oriental Basin. Here, LRO's terrain map combines with surface gravity measurements from the Grail mission. This data reveals structure in the lunar crust beneath the surface, giving us a window into the geologic features of the moon's interior. Our next location receives little direct sunlight and has some of the coldest recorded temperatures in the solar system, the South Pole. The highlighted spots signify potential water ice based on temperature readings from LRO's Diviner instrument and reflectance from its laser altimeter Lola. Lola also allows us to peer into the darkness of Shackleton Crater by bringing us this digital elevation model. It's 21 kilometers wide and 4 kilometers deep, but it pales in comparison to the largest known impact crater in the Earth-Moon system, the South Pole Aitken Basin. Sitting on the far side, it's 2,500 kilometers across and 13 kilometers deep. We don't yet know exactly how old the basin is, but it was first seen in the 1960s by spacecraft flying around the far side. As much as we use LRO data to investigate areas we can't see from Earth, we also probe familiar territory on the lunar near side to bring back images with an all-new level of detail. This is Tycho Crater. It's around 100 million years old. Here, the Lunar Reconnaissance Orbiter camera captures the central peak with a 100-meter wide boulder at the summit, the origins of which are still a mystery. Continuing across the moon's near side, We will arrive in an area ripe for future exploration due to the diversity of impact and volcanic materials. It features a prominent crater so bright it's not only visible through telescopes, but also to the naked eye. Welcome to the Aristarchus Plateau. Here, infrared shows the mineral pyroxene in orange and a splash of plagioclase in blue from Aristarchus crater. This region can tell us a lot about the rich volcanic history of the Moon. As much as we study the Moon looking for sites to visit, we also look back at places we've already been. This is because the new data that LRO is gathering helps us reinterpret the geology of familiar places, giving scientists a better understanding of the sequence of events in early lunar history. Here, we descend to the Apollo 17 landing site in the Taurus-Littrow Valley, which is deeper than the Grand Canyon. The path the astronauts took over the course of 3 days is shown. The Lunar Reconnaissance Orbiter camera is even able to capture a view of the bottom half of the Apollo 17 lunar lander, which still sits on the surface, as well as the rover vehicle. These images help preserve our accomplishment of human exploration on the Moon's surface. Moving onward, we make our way to our final destination. This location contains regions that exist in permanent shadow, as well as ones that bask in nearly perpetual light. It's the North Pole. Detailed terrain measurements by Lola allow scientists to model sunlight and shadow at the poles over decades and centuries. Sunlit peaks and crater rims here may be ideal locations for generating solar power for future expeditions to the Moon. This updated visualization of the lunar landscape stands as a testament to the functionality and abilities of the Lunar Reconnaissance Orbiter spacecraft. And as the mission continues to gather data, it will provide us with many more opportunities to take a tour of our Moon.
Thanks, Brian. Thanks for sharing that. Some of that imagery was really incredible. I'm surprised at how fine a resolution some of those images have. All right. Up next, we've got Chuck O'Dale with his presentation, How We Learned to Love the Bolides Until It Was Too Late. So you can advance the slide.
There we go. Signed the dinosaurs. They had a nice trip for a while. And they did love the bolides, trust me. I'll show you how they did that until it was too late. Anyway, I just want to point out apologies to Stanley Kubrick and Dr. Strangelove. I don't know if you've seen the movie, but it takes a genius to make a comedy out of nuclear Armageddon. You did okay. I love that movie. Anyway, speaking of Armageddon, what we're going to do, I'm going to first review how the dinosaurs disappeared right at this point here at the 65 million year point. But right after the Permian extinction, right here, there was a period of time where the dinosaurs, the amphibians, the reptiles, and us mammals all lived happily together, fighting for the top of the food chain. And then suddenly, right about here, something happened. I'm going to get into that. There's a whole bunch of stuff happened there that caused the dinosaurs to suddenly erupt into the size that they had. At this point, right after the Permian, the reptiles were actually the dominant species. And the poor dinosaurs and the mammals, we were sort of running around trying to stay out of their way. So what I'm going to do, I'm just going to review what happened at this point and compare what happened there to all these points. I'm going to give you a quick presentation here at the end, and I'll leave you with a conundrum at the Permian. But first we'll get into the Cretaceous Paleogene. So that's what our planet looked like at the time. and the dinosaurs were living very nicely between the beginning of the Jurassic right to the end of the Cretaceous. And they had a 130 million year good time on this planet. And then suddenly, we had this big explosion, the Cretaceous, the KT boundary, the Chicxulub crater, 150 kilometers across. And it caused a worldwide, pretty well, Armageddon. Anything bigger than a house cat did not cross that boundary right there. So at this point, the non-avian dinosaurs went extinct, and we now have all the avian dinosaurs flying around. About 10,000 plus species of dinosaurs we still have with us. So, aside from the crater, we had a worldwide kind of deposit from the crater. There's actually two kinds of deposits. There's about a 3 millimeter layer around the whole planet. And it's called the old KT boundary here. And it's found pretty well anywhere on the planet. If you go to the RASC this year, I think there's a tour to see the KT boundary. And the other, as I say, there's a 3 millimeter layer all the way across the planet. But as you get closer to the crater itself, what you have is the debris, and the KT boundary gets thicker and thicker until right on the Yucatan Peninsula, they got some pretty thick layers of it. And it contains tektites and a lot of iridium. So, aside from the crater, the impact, we also had a lot of volcanic activity going on this planet called the Deccan Traps. Now, when the Chicxulub impact happened, it shook. There was quite a big earthquake event around the whole planet. And this area here had a sudden eruption of a lot of lava. And apparently there's a paper just out that describes a KT layer of lava caused from the earthquake from the Chicxulub impact. And it's called the antipodal, I guess. The Chicxulub impact happened around the Yucatan Peninsula, just on the other side of the planet, is around where the Deccan Traps happened. So you can see the earthquake sort of propagated around to the other side and shook loose a whole bunch of lava in India. So not only do we have the KT boundary, but we have the iridium spike, right on the KT boundary. The iridium is a natural element in the planet. There's probably 3 parts per billion naturally. And within the KT boundary, there was 3 parts per million. So it's almost 100 times the normal background. And Dr. Alvarez, just over here, and his son, they first of all documented the KT boundary at Gubbio in Italy. And if you ever get a book you want to read about the scientific method, they published a book called The Crater of Doom. And it sounded kind of hokey, but it was a very excellent documentary on how the scientific method works and how they actually determine where exactly the crater was. That's another story. But anyway, that's the essentially what happened right at the end of the Cretaceous, when the non-avian dinosaurs, they did not make it across that boundary. Anything larger than a house cat basically didn't make it. So after that, essentially this was us from the Paleogene on, 66 million years, and here we are at the top of the food chain. But that was a little fella that survived, and obviously we did okay. So, what happened on the Triassic that is so important to the dinosaurs? Well, as I mentioned earlier, the reptiles were the dominant species from the Permian extinction right up to the end of the Triassic. And something happened, actually a whole bunch of stuff happened. And there's all kinds of hypotheses. And it's strange, when I started researching this, probably in the middle of last month, you know, you fall into the rabbit hole on in the internet. But this month, there's 2 brand new papers about this very subject. So I'm going to quote some of the stuff from those papers. But if you have a chance to pick up this month's Scientific American, it has an excellent article on this subject of the end Triassic. What happened to make the dinosaurs the dominant species between the Triassic and the Paleogene. So these are fossils of the reptiles and the amphibians, actually. They were gigantic back in those days. And the dinosaurs at this time were probably the size of a house cat, and the mammals are a little bit smaller. But we're all scurrying around. Basically, it wasn't the survival of the fittest, it was a survival of who could run the fastest. And this was a example of what was going on in the Triassic, in the reptile species. Now there's probably about 10 species left of the reptiles from that era. And the dinosaurs still have maybe 10,000 species flying around here. So the dinosaurs are still almost the dominant species here. So what happened in the Triassic to make the reptiles give up the top of the food chain? Well, let's go into a few things that did happen there. I mentioned a lot of stuff that happened on the Cretaceous. And let's start off with impact craters. I think I've told you before, I kind of explored them once in a while. First one I'd like to document is the Manicouagan, right? It's almost right on the Triassic-Jurassic period, the barrier there. And when I first saw it from the air, you could just see the length of this. This is almost 80 kilometers here. It's kind of cool. It just blew me away. This is from my old analog camera. And it just blew me away how big the thing really was. So my good buddy Eric and I, we actually went in there and explored it. So to give you an example of the size of the trench here across, I encoded this picture. The trench goes, you know, how big that is. And that's only the width of it. The length of it just goes down here. Well, as I say, Eric and I, we went in and we did explore the Manicouagan. We explored all the way through here on this canoe. And we were marooned on this island on the way back. We started off from about here, nice and calm. By the time we got out here, the wind went from 0 to over 20 knots, so you can see the waves up there. And the size of the canoe versus the waves, it gives you an idea. So we had a canoe full of rocks. What could possibly go wrong? Anyway, here we were on this island. Nobody knew where we were. Nobody, anybody. And so we had enough food for at least 5 days. We would have survived. And lots of water, of course. So, but I can tell you that if it wasn't for Eric's expertise on a canoe, I don't think I'd be here talking about it. But it sounded like a real good adventure at the time, but looking back, we had a close call. We really did. But we got off the next morning, and within 5 hours of canoeing off this, we were having bacon and eggs in a restaurant, thinking, what a great time that was. Anyway, that was Manicouagan. So I'm going to document a few of the craters that happened during this period. Oh, I just want to mention our sesquicentennial crest here. That is actually the depiction of the Manicouagan crater. There is a good description of what exactly is all in the crest on the website. It's kind of cool. But I'm glad they included Manicouagan. And of course, the St. Martin in Manitoba. This is a neat one here. If you look at the image I took right here, that the crater rim is right about there, and this river, the Dauphin River, comes up and makes a 180-degree turn. And it's Chuck's hypothesis that it's the case of the crater rim that caused the river to do that. It hasn't been geologically confirmed yet, but I'm sticking with my hypothesis. And then there's Red Wing further in the States. I flew over that. Basically, it's buried within under a kilometer of dirt, but the crater is there. And they have drilled into it and confirmed beyond a doubt that it is impact. In France, all around this time here in in the Jurassic time is where these impacts happened. That was in France, in Finland, in Russia, and Odessa. So that's, if you look at it, you think, well, why are the craters just grouped there? Well, that's only a third of the landmass. And maybe 2/3 more craters actually happen in the oceans. So, and this area here of South America, Africa, and Antarctica have not been explored extensively as North America has. So I am sure more craters from that era is going to appear eventually from there.
John, what's the time span between the first and last of those?
Yes, I'm going to get into that later, but it's not exact. I'd say you're looking at maybe 30, 25 million years in that era. And this is why I say there's a lot of stuff that happened there. The extinction itself, there are hypotheses, the fact that there is not a Triassic-Jurassic extinction itself, it's just a gradual happening over this 30 million year period. So first part I want to document is the craters that happened there. And basically the dinosaurs were secondary to the reptiles, and then after these impacts, the dinosaurs finally became the dominant species. And I mentioned the KT boundary from the Chicxulub. The Manicouagan crater actually has a debris boundary as well, and it's found in England. And apparently they found a new quarry full of these this debris. So I'm going to be looking into maybe getting a piece of that. But that's the KT, the only boundary or the only debris field from the Manicouagan or any other crater from that time. But you have to look at the fact that you're looking at 200 million years ago versus only 66 million. You know, that was yesterday. So there are two areas of volcanic activity. I mentioned the Deccan traps for the dinosaur extinction. We had what's called the camp here, and just write this down here. It is called the Central Atlantic Magmatic Province. Essentially, it's one of the biggest provinces of volcanic activity on the planet, and it happened right at this barrier here. So this is another factor that caused the climates to change. The Manicouagan, there is a few papers out that document right around the time of the Manicouagan, there's a layer of lava within this camp volcanic activity. And it has been documented right in the Bay of Fundy. If you ever get down to the Bay of Fundy, up to this Cape Spit here, it is an awesome cliff. And this is actually part of the Manicouagan magmatic shakeup from the earthquakes from the impact. Here, Julian and I actually flew over Cape Spit. You actually see the cliffs here. It's pretty cool. It was really neat to see. And if you ever get there, there's a parking lot right about here. It's a 5-kilometer walk into it to get to the grass knoll there. And don't fall off the cliff. It's about 200 feet. But it's really cool to see. And there was an iridium sort of spike right in that layer, right by the Manicouagan. Right in this layer here, there was a documented iridium spike. Not as big as the KT boundary, but it was noticeable in the data. And another volcanic activity, not too many people, I didn't know about it until I researched this paper, but we had a volcanic province actually collide with the west coast of Canada in the United States here. And this area caused well, maybe not caused, but there was a major climatic change right at the time this volcanic activity was happening. And right after this climate change was when the dinosaurs suddenly erupted into larger sizes. So there's all kinds of connections here. The impacts, the volcanic. So as you just say the hypothesis just continues. The deeper I went into the rabbit hole of research, the more I found out. But right at the time, as I mentioned, this is the Triassic here. Right at the beginning was this volcanic activity, and it caused a large climate change to cause the dinosaurs to gradually increase in their size as they went through the Triassic. So we had the impacts, the volcanic activity that happened there, but nobody can, beyond a doubt, show exactly the causal effect of the dinosaurs getting bigger. All we can say is that this climate change, the dinosaurs suddenly began to grow bigger. The reptiles slowly lost their diversity. And you can notice that it's not exactly right on the boundary. This volcanic activity here happened here. So the hypothesis is that it's not a extreme wall, it's actually a gradual change. And these are the hypotheses that are coming out as we speak. But the comparison between the KT and the Jurassic is striking, the way things happened. But the dinosaurs definitely grew larger at this time. So, as the impacts were happening, I guess the dinosaurs are saying, whoopee, bring them on. But, of course, they didn't have a space program, and unfortunately, the non-avian dinosaurs didn't cross that boundary. So they had a 135 million year ride on our planet, though. They were the dominant species for this whole 135 million years. It was kind of cool. But they didn't have a space program. And hopefully we will, to be able to save ourselves. So I showed you the comparisons between the KT and the Jurassic. I'm just going to show you a couple of others here. Of course, whoops, where are we here? At the end Permian, did I go too far? Oh, okay, we had the Jurassic. The end Permian has a large, the volcanic traps, the Siberian traps in Russia. And these guys were coincident with the Permian extinction. At this time, almost 90% of all life on this planet disappeared. This is the only item that we know of that happened at that time. But I'm going to leave you with this. Whoops, I'll just go down a couple here. In Antarctica, there is a large magnetic or gravity anomaly. It's about 500 kilometers across. It hasn't been researched yet, but the hypothesis is if that is an impact, the Siberian traps was right on the antipodal of that event here. So that's something to think about. It's not, cast in stone, but at the same time, it's something we're looking at. I'm just going to go back a couple. I also mentioned that not only a whole bunch of stuff happened here, but right at the Jurassic Cretaceous, it's not so much an extinction as kind of a climate change. Some species got less diversified and so on. Some dinosaur species did disappear and some appeared. And it's about that time that the Tyrannosaurus got a little bit bigger. But the volcanic activity was right on the junction of Africa and South America. And it was a fairly large one. And the bolides, again, there was some major bolide activity on our planet at that junction here. And again, the dinosaurs were saying, hey, bring them on. So, my conclusion is, yes, we're on the top of the food chain for now. That's all I can say. But this, I love this picture here. This, that's a dinosaur, without a doubt. So I'd like to conclude my talk by saying that, remember, we're in a shooting gallery. And fortunately, we're going to have a space program because let's hope these guys keep flying past us. Thank you very much.
Thanks, Chuck. As always, that was fascinating. Okay, so we're going to go to break. Okay, everyone, welcome back. We're going to welcome Dr. Robin Fiore up to the podium. She's going to give us a talk on the dark side of the aurora, how space weather affects technology.
Hi, so my name is Robin, and I come from the Canadian Space Weather Forecast Centre, which is a part of Natural Resources Canada, so of course I have to use their templates because technically this is a work talk. But I hope that you find it interesting. Not a lot of people are really aware of what space weather is, but all of you, I'm sure, are aware of the aurora. So dancing overhead, the aurora have really awed and inspired humanity for centuries, for millennia even. Ancient cultures have incorporated aurora into their myths and their folklore. We see writings and depictions of the aurora for hundreds and thousands of years. Most of the time, if we go back in time, we notice that a lot of the mythology portrays the aurora as having kind of a negative connotation, being a sign of plague, of death, usually some kind of war. And if you think about it, this is a bright light in the sky, and if you don't know what's causing it, it can be really scary. But it's really interesting to know that the source of the aurora is celestial. It comes from the sun. It's something that we need to be aware of. Now, the aurora are just one of the effects of the complex relationship between the sun and the earth that we call space weather. Now, space weather describes a collection of physical processes beginning on the sun and ultimately impacting activities on Earth and in space. And we'll talk a little bit more about what this means. Space weather is a hazard of the technological age, and it's becoming more of an issue as our technologies become more and more sophisticated. And Canada is one of the countries that is most impacted by space weather because of our location. So it's particularly important that we be aware of it, because there is a lot of social disruption and economic loss that can happen. Now in this talk I'm going to give you a brief history of the aurora because I think it's quite interesting. But I'm also going to talk about what space weather is and some of the technologies and the infrastructure that are impacted by it. So here we see the aurora. Now, the aurora are called the northern lights. In the northern hemisphere, they're the aurora borealis, and in the southern hemisphere, they're called the aurora australis. And aurora and borealis are named after Roman and Greek gods. And it wasn't until the 1600s when those names were actually put together to be called the northern lights, or the aurora borealis. Now, there have been many theories as to how the aurora are formed, but it wasn't really until 1902, 1903 when we determined the link to the sun. And this was determined by Christian Birkeland, who's someone quite famous in our field. Over 100 years later, following the work of many international scientists, we have a better idea of what causes them. So we know that the sun is constantly ejecting streams of charged particles. These particles come towards the Earth and they're trapped by the Earth's magnetic field, and then they're guided towards the magnetic poles, so in the northern hemisphere and in the southern hemisphere. And when these electrically charged particles collide with particles in the Earth's atmosphere, it can cause light to be emitted. So this is the aurora. Typically the aurora is green like we see here, but it can also be red and in very rare cases kind of a bluey purplish color. Now, most polar cultures have myths and legends about the aurora, and this is just simply because they feature so prominently in their lives because of their locations. So North American cultures have maybe the most varied history with the aurora because of the vast number of cultures on this very large continent. So here we can see a picture of what the Inuit thought the aurora was, and they attribute it to the spirits of the dead playing football with a walrus skull. Other cultures reversed this and pictured it as walruses playing football with a human skull. Kind of interesting. Most typically, the aurora is seen as spirits of the dead trying to communicate with the relatives that they left behind. More sinister folklore sees it as demons carrying lanterns going out to capture the souls of the lost. In Norwegian cultures, over here, they thought that the aurora was caused by the reflection of the shields of the Valkyries carrying the dead who died in battle to Valhalla. In Finland, the word for the aurora roughly translates to foxfire, and they saw the aurora as being caused by a fox running through the north and sweeping snow and sparks into the sky, which is kind of a nice picture. People have all sorts of myths as to how you are to treat the aurora. If you whistled or clapped at them, the Sami cultures believed that you might attract them and they would come down and snatch you and take you away. But if you clapped, you could scare them away. Women once believed that if you gave birth under the aurora, it wouldn't be painful, where others believed that if you stared at the aurora while pregnant, your children would be cross-eyed. Some of the most interesting cultural beliefs come from the Chinese. In China and Japan, they believed that the aurora was caused by dragons fighting in the sky, and they believed that a child who was conceived under the aurora would have good fortune. And based on northern tourist industries today, this belief still seems to be in effect. Moving on. Because the aurora features so prominently in our folklore and our mythology, it's not surprising that we've seen it throughout our history. So this is the earliest known depiction of the aurora. It comes from 30,000 BC. It's a Cro-Magnon cave painting. Excuse me. I don't really see it, but apparently that's the aurora. We'll trust the experts there. The earliest known writing of the aurora comes from 2600 BC in Chinese literature, where it's depicted as lightning illuminating the sky. And here, thousands of years later, in the 1500s, we see pictures of the aurora being depicted as candles above the clouds, excuse me, and as fires in the sky. So this picture comes from Nuremberg, and that is from, I think, 1570 AD. Now, the aurora are often seen as having a negative impact, like I've said. This typically comes from cultures at lower latitudes where the aurora isn't seen as often, and when it tends to have a very blood red color. So this would be very ominous in appearance. So the aurora has been said to foretell a number of significant events in history. So this would include the death of Julius Caesar, birth of Muhammad, earthquakes and famine in Europe, the Civil War, the French Revolution, and even parts of World War II. Now, we tend to dismiss a lot of these kinds of claims right now. Regardless, the aurora has shaped history, and it's caused some significant events to happen. In 340 BC, a nighttime infiltration of a city was said to be stopped due to lights from the aurora. There are a number of cases where people have thought the aurora was actually a forest fire or a fire in a city. So in 37 AD, Tiberius actually sent the Roman army to put out the Black Forest, thinking it was on fire. There are cases in Salzburg, in Geneva in the 1920s, and in 1938, firefighters were called all over Europe to put out fires, believed to be the aurora. So a lot of the times, these sightings of these blood red auroras have been seen to be caused by some kind of some god punishing or looking down on us. And it's really only been recently that we understand that the celestial source of the aurora is actually appropriate. And this, the aurora is actually a sign of a potential hazard here on Earth. And this is caused by space weather. Sorry, I've got a bit of a cold. I'm sure you can tell. So moving on, space weather is as old as the sun, but we've really only been aware of it since the mid-1800s when it made a media debut, interfering with the telegraph system. Since then, it's interfered with all sorts of kinds of technology and infrastructure. And this is caused by the sun, ultimately, and we call this space weather. It's really become an interest in the media because right now we're becoming more aware of its effects. and we're becoming really interested in what we call the 100-year storm and the kinds of impacts that it would have on society today. So just like we go to Environment Canada or the Weather Network for information on terrestrial weather, you come to the Canadian Space Weather Forecast Centre for information on space weather. I'm getting a little bit ahead of myself, but I'm going to introduce that to you a little bit later in the talk. So earlier, I told you that space weather is a collection of physical processes beginning on the sun and ultimately impacting activities on Earth and in space. What does that mean? Basically, we're talking about the ways that the sun impacts us beyond causing our temperature to rise or drop and beyond causing us to have to wear sunscreen. There are particles continuously coming out from the sun. There's a magnetic field that comes out from the sun, and those all impact us. And the way that it impacts us is what space weather really describes. So space weather ultimately begins on the sun, so let's begin there. The sun is continually ejecting high-speed streams of electrically charged particles. And these particles stream out from the sun, and they carry with it a part of the solar magnetic field. And this is called the solar wind, and the magnetic field's the interplanetary magnetic field. The sun is also emitting energy in the form of radiation. So as the particles in the magnetic field come towards the Earth, they can interact with the Earth's magnetic field and the upper atmosphere called the ionosphere in very complex ways. These lead to currents being formed and particles to collect in different parts of the ionosphere. And this leads to geomagnetic disturbances and ionospheric disturbances. And this is really the impact that space weather has on the Earth. And these disturbances will then in turn impact technology. Now, I'm going to be showing you some images of the sun, just like this one here. They come from the Solar Dynamic Observatory run by NASA, and the Solar Heliophysical Observatory, which is jointly run by NASA and the European Space Agency. So these are satellites that are observing the sun. They have these great images, but you're going to notice that they're different colors, and that's just because there's different filters over them so that we can see different kinds of activity and features. Now, there are three basic kinds of solar phenomenon that have major impacts here on Earth. These are solar flares, coronal holes, and coronal mass ejections. So the first one I'm going to talk about is a solar flare. So here you can see solar flares here and solar flares here. And what these are the emission of radiation, mostly in the form of light, but also X-rays and EUV radiation. So the magnetic field that's on the sun is really complicated. It becomes kinked and twisted, and energy stores up, and it comes out in this burst of light. Now, we can see these as a solar flare, and they typically last anywhere from a few minutes to maybe up to 2 hours at a maximum. Solar flares are categorized according to their strength. The lowest flares are A, B, and C flares. A moderate flare would be a class M flare, and a major flare would be a class X flare. So these are caused, this one here is an M5 flare, and this one here is an X2 flare. Now these can have impacts on the Earth when the radiation comes to our atmosphere and basically causes it to thicken. And that's going to influence any kind of signal that travels through the ionosphere. Now, solar flares have caused the end of the world in Hollywood many times. It's usually depicted as a ball of fire raining down on the Earth, but this isn't what it is at all. A solar flare is purely radiation, so it would be something you see, something you can measure with X-rays. So moving on, we have coronal holes. This is the second solar phenomenon that would be of importance for space weather. So a coronal hole is basically a region on the sun that you could say is magnetically open. So we have particles that are streaming out from the sun in a coronal hole. Usually that plasma is moving faster than the background solar wind. Because it's moving faster, when it reaches the Earth, the magnetic field is going to fluctuate. And those fluctuations will cause currents to flow, cause particles to be distributed, and it's basically the magnetic field getting used to that extra particle contribution. So they get their name because they actually look like holes on the sun. So here we see a coronal hole stretching down the entire sun. Here we see a coronal hole that's taking up most of the southern hemisphere of the sun. Now this coronal hole in particular is quite interesting because it caused the failure of 2 Inuk satellites in 1994. And this was very significant because they were responsible for telecommunications in the north. And northern Canada was essentially cut off from the rest of the world for at least 8 hours while these satellites were down. I'll talk about that a little bit more later on in the talk. And then the third solar phenomenon, and perhaps the one that most affects the Earth, is called a coronal mass ejection. Now this is a massive ejection of particles. We're talking 1/8 the mass of the moon at the upper scale. So these particles will explode out from the sun. They're going to be coming towards the Earth in a cloud of particles, and they're going to be dragging along part of the solar magnetic field. And these particles can have major impacts on the Earth because of the speeds at which they move. So the normal solar wind is moving at about 400 kilometers per second, but these coronal mass ejections can move it up to 2,000 kilometers per second. So the particles coming from a coronal mass ejection are going to impact the Earth in 2 waves. The first wave of particles is caused by protons. These are accelerated to near relativistic speeds, and they reach the Earth in about 1 to 3 hours. And they can impact the Earth, primarily the ionosphere and the high latitude regions on the day side. The bulk of the plasma comes 1 to 3 days later, depending on how fast the coronal mass ejection is moving. And they're going to cause impacts on both our magnetic field and the ionosphere, mostly on the night side. Now, the sun is a sphere, and coronal mass ejections can be ejected from any point on that sphere. But we're, excuse me, we're only interested on the explosions that are coming towards the Earth. So if an explosion is coming towards the Earth, we're going to see a ring around the sun because all those particles are coming towards us. You can see kind of the outer boundary of them. So that's the ring that you see here. And that's called a halo CME. This was a massive CME that took place Halloween of 2003. This is a pretty famous event for space weather scientists because it caused some pretty major impacts. This is another CME that took place in February of 2000. This one just shows you an example of a CME exploding upward from the sun, so this one wouldn't have had very strong impacts on the Earth. But it's interesting to see it explode out. It's really great that we have these images that we can go back to determine exactly what's happening on the sun. And we can see them relatively quickly. So these phenomenon are not going to impact us until they reach us. For the most part, the solar particles in the solar magnetic field for the most part, we're protected from these by the Earth's geomagnetic field. So that's what we're going to talk about for a slide here. So the geomagnetic field mostly resembles a dipole, okay? If we were to take a bar magnet and put it right into the middle of the Earth, tilt it by 11 degrees, and shift it by about 550 kilometers from the center of the Earth, we could actually account for 90% of the Earth's magnetic field. And we actually use this to simplify our equations sometimes. Realistically, it's a little bit more complicated, obviously. So you can think of the geomagnetic field, like I said, as a force field. Without that force field, our atmosphere would be stripped away, and we wouldn't have an atmosphere life wouldn't be possible. Now, the magnetic field, like I said, is a little bit more complicated than a dipole, simply because the solar wind and the solar magnetic field are constantly streaming past it. And because of that, our magnetic field tends to be compressed and rounded on the front side. And this is called our magnetosphere now that we're talking about it being distorted. So that's the front side magnetosphere, and we have the sun over here somewhere. And here we have the magnetotail, and it tends to be elongated, and it comes to a point, say, 50 to 100 Earth radii away from the Earth. So it's quite large. I just want to take a little aside here. This is something that's kind of interesting. Because our magnetic field is constantly changing, the location of the North Magnetic Pole is constantly changing. So right here, we're not actually talking about contributions from space weather, we're just talking about the magnetic field itself. So that geomagnetic field is caused by movement of the molten outer core of the Earth. And because that outer core changes slightly over the period of millennium, the location of the North Magnetic Pole is also changing slightly. So here you can see where it's moved from 1831 to 2007. And 2007 was actually the last time it was measured. And here's one of my colleagues. This is actually a 2001 measuring of the North Magnetic Pole. We can't measure it anymore because it's too far away from any landmass. It's just not possible to take an expedition out there even by helicopter. It's not practical anymore. But there are hundreds of magnetometers, which are instruments which measure magnetic fields. They're located on the ground. They're also located on satellites in space. And we can take measurements from these instruments in order to model the magnetic field to determine where it is. So we know that the north magnetic field, as of earlier this week, was about here. So you can see it, interestingly, it's been making its way over to Russia pretty steadily. We don't know if it's going to continue doing that. It could turn around. Magnetic fields can even reverse so that the north and the south poles are at opposite ends of the Earth again. Right now, just to make this motion kind of easier to understand, it's moving at about 130 meters per day, which is pretty impressive. So, back to the talk. Space weather is kind of a concept that's difficult to understand. It's hard to relate to. It's involving invisible forces and invisible particles that we can't see. Terrestrial weather, we see a tornado, we see a thunderstorm, we can hear it, we can smell it, we can feel the wind. We can't really do that with space weather, but we can see the aurora, we can see the northern lights. And the interesting thing about the aurora is the way that it's formed, the way these particles are funneled in towards the Earth's magnetic field, or are funneled in by the Earth's magnetic field towards the Earth. The aurora are going to occur in a regular region, and they actually form an oval around the geomagnetic pole, which is the pole that's actually caused by that dipole field that is quite important. So here you can see satellite imagery of the aurora here. Here you see the active region where the aurora is over Canada. So the interesting thing to note from this diagram is that if you look at where the auroral oval is, Canada is actually the country that is most covered by the aurora if you're looking at landmass. And as activity increases, when we have a space weather event, that oval will actually become wider and it will cover lower latitude areas, even stretching down into the United States. So whenever we see the aurora in places like Ottawa, where we don't typically see it, this actually means that there's some kind of event going on, and there's a potential for hazard, potential for impacts to technology and infrastructure that are sensitive to the aurora. So moving on, let's start to talk about the impacts of space weather on technology. So just to kind of describe this image, here we've got a complicated sun. It's ejecting particles towards the Earth, and here we have our geomagnetic field, and it's going to be influenced by these particles. So there are a lot of technologies on Earth that are actually sensitive to space weather and space weather impacts. I'm going to be talking about a few of them, namely power systems, pipelines, HF radio communication, which is used by the aviation industry, any kind of infrastructure or technology that involves a compass, so this would include directional drilling, even the use of compasses in agriculture, aeromagnetic surveys for mineral exploration, and of course satellites, which are located directly between the Earth and the Sun. So the first infrastructure I want to talk about is actually the telegraph, and that's just because this was the first kind of technology that we observed space weather impacts to. So whenever you have fluctuations in the geomagnetic field, this causes currents to be induced. And these currents can be induced in any kind of long conductor. So the earliest long conductor that we knew of was the telegraph. So these currents would flow in the telegraph lines, and they would have a variety of impacts. These could be quite minor, to just changing a few characters in a message, to sending a completely nonsensical message. Operators reported damage to themselves, burns on their fingers, or numbness in their hands. Fires were started in telegraph buildings. And my favorite impact would be the telegraph system working perfectly normally without being hooked up to any kind of power source. The aurora is actually an amazing source of power, and if we could harness that, we wouldn't have any problems. The only problem is the aurora is finicky and it's not constant. You can't really rely on it. Another long conductor that we sometimes forget about is the railway system. This is a particular problem in places like Russia, where the railway system runs in the east-west direction, and that's because these currents tend to flow in the east-west direction. There have also been reports of impacts to the railway system in Sweden. Now, we don't actually see sparks on the railway lines or anything like that, but what we do see is problems with the circuitry along the railway lines. And the key problem that we would note would be false reports of blockages on the lines. And whenever there's a reported blockage, of course, the railway system has to stop. It has to be investigated. This causes an enormous a cost, of course, because of the time lost and the impact on connecting trains. And of course, the biggest infrastructure that we are dependent on would be power systems, okay? So these same currents that can be induced in the telegraph and the railway systems can also be induced in power systems. Fluctuations in these power lines are generally within the norm of what the system can handle. But there are cases where fluctuations are big enough that they move outside of what would be considered normal operation. Now, within the auroral oval, we expect to see a lot of fluctuations in these current systems just because of the aurora being there. But there are cases when we have a large event and the aurora expands to lower latitudes. And when this happens, systems that perhaps aren't as used to seeing these kind of currents are exposed to these strong currents, and they're quite vulnerable. So this can be a particular problem at lower latitudes whenever we have an extreme event. Now, the damage caused to a power system can be quite varied. We can have damages to transformers. So here we have a transformer that's burnt out. We can have a simple tripping of a line, or we can have, in a worst case scenario, a complete blackout. Now, damage to transformers is what the power industry is particularly interested in, because these transformers are huge. So here's an example here. They're massive pieces of equipment. They're extremely expensive. They take over a year to build and ship. And for the most part, they're not made in North America. They're made in China. There's a lot of concern that in a massive event, an extreme event, the 1 in 100-year event, that it would cause multiple transformers to be burned out. And there's a lot of concern, and a lot of research shows that we might not be able to recover from that within our lifetimes. Okay, maybe not even within our children's lifetimes. It would be extremely expensive and extremely difficult to mobilize these kind of systems, especially without the power industry, or without the power infrastructure working. And the most famous example seemed to froze here. Can we advance the slides without the? Yes.
Solar flare.
Yeah, solar flare. Oh, there we go. Okay, actually that wouldn't be a solar flare, sorry. Coronal mass ejection. Okay, so the most famous event would be the blackout of the Hydro-Quebec system, March 13th, 1989. Some of you probably experienced that. So this was a really interesting event. Here we have the Hydro-Quebec power system. We have power being generated in James Bay and Churchill Falls, and it's mostly being used in the Montreal and Quebec areas. So during this event, we had 2 large coronal mass ejections, ejected, I think March 8th and 9th, or 9th and 10th. They basically piggybacked on each other, caught up in between the Earth and the Sun, and they hit the Earth around the same time. So this caused quite a large event. When this happened, the auroral oval expanded so that it was right over top of the Hydro-Quebec power system. So massive currents were induced in the system. It caused lines to trip, particularly in the east-west direction, over the system. Now, normally the auroral oval would be up here, not a problem. When these lines tripped, it cut off the power being generated from their main load. The system was overcome, and of course, caused a blackout. So the blackout impacted 6 million people for 9 hours. This was in March, but imagine if this had happened in the middle of January when it was quite cold. There could have been fatalities caused by this. I don't know if there were fatalities from this. I wouldn't be surprised if there was, but it did cost the Quebec economy and utility companies millions of dollars to recover from this. Now, the transformer that I showed you in the previous slide that burnt out was actually from the Hydro-Quebec blackout. Now, even though I gave you all these warnings about transformers, there did happen to be a backup transformer for this particular transformer, fortunately, and it was easy enough to move into place, and the system was recovered. So there's a lot of interest in our community right now to model these induced currents into the power systems to try and determine what needs to be done in order to make sure that they don't lose operation. So now we move into pipelines. Pipelines are another example of a conductor that can be impacted by space weather, by these induced currents. So pipelines are subject to corrosion. And corrosion is an electrochemical reaction. So when you have currents flowing in the pipelines, it can cause increased corrosion. Now this is something the pipeline industry is very aware of, and they have corrosion protection devices on the pipelines. But anytime you have these fluctuations, it can compromise the operation of those devices, and it can make it appear as if corrosion is happening when it's not. In some cases, it can cause corrosion when it shouldn't. So this can either cause a very costly investigation to determine if the pipeline is indeed corroded, or it can reduce the lifetime of the pipeline. Now we're not talking about a coronal mass ejection causing a pipeline to burst. That's not what happens. But it could cause a pipeline that's supposed to last 80 years, last 65 years. Okay? So we're still seeing a cost impact due to that. The next system that I want to talk about is satellites. Now satellites are particularly vulnerable to space weather because they're located right in between the Earth and the Sun. So whenever we have energetic particles coming from the Sun, they can penetrate through the skin of the spacecraft, and they can have a variety of impacts. These can range from false commands being issued, to physical damage to the system, to a buildup of charge with a subsequent discharge causing problems to the satellite. So here we see an example of that. This comes from the Solar Heliophysical Observatory, and it's viewing the Sun. And here the snow is actually caused by solar protons moving through the satellite on their way to Earth. And we typically see these after coronal mass ejections, and it's one of the ways that we can tell if a coronal mass ejection is directed towards the Earth and is likely to impact us. When we see them here, we would expect to see an impact within maybe an hour on the Earth. Another satellite that was impacted by space weather would be the Inuk satellite, like I said, in 1994. So what happened here is we had this buildup of particles over a period of 7 days. Eventually, they penetrated the spacecraft shielding, and they caused a charge up of particles and then a discharge, which led to the loss of the momentum wheel in the satellite. So there were 2 satellites that began to spin out of control. One was recovered, fortunately, after about 8 hours, and the other one wasn't recovered for, I think, 9 months. And what Telesat really had to do is they had to build an infrastructure of instruments across Canada to try and contact the satellite. So satellites are very expensive to fix. We can't send up a crew to go fix a satellite. So it's a major loss if a satellite is sent out of control due to a space weather event. And there are a number of satellites that have been impacted by space weather. Unfortunately, we have a lot of trouble getting statistics on that because companies don't want to release those statistics for obvious reasons. So moving on, HF radio communication. This is actually the part of space weather that I'm studying right now. So whenever we have impacts on our ionosphere, which is an upper layer of the Earth's atmosphere, that's going to impact any kind of signal that has to either reflect off of the ionosphere or refract from it to bounce down to the Earth to be heard, or any kind of signal that has to travel through it. So HF radio communication, we see a radio signal that bounces between our transmitter and the ionosphere back to the ground, and it can do that multiple times in order to be received on the ground. HF radio communication is also often used by the aviation industry to communicate, particularly at the most polar latitudes where satellite communication is more difficult. And when this happens, the ionosphere basically absorbs the radio signal. So a signal that would normally be transmitted between an air traffic control tower and the airplane would instead be absorbed by the ionosphere and not heard. So this is something that is becoming more important as more and more polar flights are passing through these high latitude regions where they don't have access to other kinds of communication. And the cost of rerouting a flight due to a space weather event is enormous. And those costs come from the increased flight time. Maybe the path they're taking prevents them from taking extra people, or extra cargo. Oftentimes they'll have to land to refuel or to change their crew because the flights are so long. So obviously this is something they want to avoid. So aircrafts are the aviation industry is very interested in a forecast of these kind of space weather events. I just want to give you some information about the relevance of this in society and having accurate information about space weather. In 1967, you can see the headline here, Sun Watchers Stopped World War III. There was an incident in 1967 where there was interference with the early ballistic missile warning system. And this could have been caused by some kind of natural occurrence, it could have been caused by a problem with the equipment, or it could have been caused by Soviet subterfuge. The first two can be investigated and fixed, and of course the last would lead to nuclear war. So over a 30-minute period, while jets were being fueled and prepared for takeoff, scientists examined images of the sun to determine what caused this, and it actually turned out to be a space weather event. Crisis averted. You might think that a lot has changed since 1967, but no, HF radio communication is still impacted. So here we see images from FEMA in the United States, Hurricane Irma in September of last year. And radio interference from a solar flare during this event actually caused interference with an early warning system in the Caribbean. It didn't cause it to go out completely, but there was some static on the system. And there was some concerns that the solar flare might be followed by other solar flares that could cause interference with the rescue operations. I'm just going to move on to GPS navigation here because I don't want to go over. Anytime we have a signal that has to pass through the ionosphere to be heard on the ground, we're going to have the possibility of impacts due to space weather from ionospheric disturbances. So GPS satellites are of course circling the Earth. They need to communicate with the airlines, for example. They want to communicate with your GPS. Whenever we have disturbances in the ionosphere, it can cause problems with this. Now the interesting thing about GPS is that GPS is not just used for navigation, it's also used for timing. Timing that's used by scientists, but also timing that's used by banks and the stock market. So we need to have an accurate picture of what's going on in the ionosphere so we can have an accurate picture of what's going on with these important systems that depend on GPS. Moving on, aeromagnetic surveys are done to aid in research exploration. What happens is we have an airplane and it has a magnetometer. It flies over the Earth, and any kind of deviation in the expected magnetic field could be caused by something in the ground. Now, it could be a buried target that could be investigated, excuse me, or it could be caused by a space weather event. So these kind of surveys can't be flown during geomagnetic storms. Excuse me. Directional drilling is actually an interesting industry that I wasn't aware of until I started working here. In order to save costs and to really maximize resource exploration, companies will often drill multiple reservoirs from a single drill head. And this is done using a steerable electronic compass a steerable drill head fitted with an electronic compass. And these compasses won't work properly whenever there are changes in the magnetic field. Now, for the most part, we might not think that this is a big deal, but when you have reservoirs and you have wells that are very close together, you don't want to be drilling into somebody else's well. It's going to have enormous legal consequences. So a lot of these companies will operate magnetometers in order to monitor the magnetic field to halt any kind of drilling that would be going on during a geomagnetic storm. So this brings us to forecasting space weather, and this is done by the Canadian Space Weather Forecast Centre here in Ottawa, which is where I work. It's actually not far from here. It's located on Anderson Road, just south of Blackbird Hamlet. So the Canadian Space Weather Forecast Centre is where we research, we analyze, we monitor space weather, and of course we provide alerts and forecasts across Canada. This is done by researchers in-house with international collaboration with industry, and with other federal departments like the Canadian Space Agency and the NRC. Now, our research includes a variety of topics. This would include the sun, processes going on there, particles located between the Earth and the sun, impacts to technology, the geomagnetic field, and of course the ionosphere. Now our compound is a 30-hectare piece of land. It's located within the green belt, very close to Merveilleux. So we have a main compound located here, and then we have a number of buildings. Some of these constitute the magnetic observatory network. Some of the buildings are used for storage, and some of the buildings are used by other groups. So our facilities are shared by other members of the Canadian Hazards Information Service, mostly earthquake monitoring. We have a number of technicians on site that are responsible for the equipment there. The compound's quite beautiful. If you're interested in seeing it, we're going to be taking part in Open Doors Ottawa on January 2nd. So you're welcome to come by and check us out. Bring your kids. We're going to have some activities for them as well. June 2nd. I keep on saying January 2nd. This is not the first place I've done it. Sorry. I really like the winter. Okay. So one of our jobs is monitoring space weather. So we have a network of observatories across Canada to monitor the Earth's magnetic field. So you can see they cover Canada from Victoria to St. John's and alert to Ottawa. Here's a few of our observatories and our equipment. We also have instruments measuring the ionosphere. I'm almost there. These are called rheometers. So they, again, are spread throughout the country. Alert is our most northern station. It's kind of an interesting place to go to. I haven't been there, but a lot of our technicians have. It's a military base. One of our technicians is kind of a die-hard Saskatchewan Rough Riders fan. He's from Saskatchewan. And he was there during one of the Grey Cups, and I think he got some of the military guys there to play football with him outside. I don't think it lasted very long. And again, you can see our station down here in Ottawa. We also share information with a rheometer network operated by the University of Calgary. We're also communicate with and work with the Geodetic Survey. So here you can see the location of GPS receivers across Canada. Our network isn't as dense as other networks in other countries. We have just as many instruments, they're just located over a larger country. And our most important product would be our space weather forecast. So we produce forecasts of geomagnetic activity across Canada in 3 zones: the polar region, the auroral region, and the subauroral region. And this is available on our website. It's just spaceweather.gc.ca. And you can get forecasts for current conditions. We forecast 24 hours in advance of the following 24 hours. Activity levels are displayed here using this kind of bar. Conditions range from quiet to stormy. Whenever there are very extreme conditions, we also issue alerts excuse me, on our website, and of course to our industry partners as well. If you play around on our website, you'll find forecasts for some of the individual observatories, and you can see hourly forecasts here. If you go to this web page, it's called our regional forecast, or sorry, our short-term observatory forecast. If you find the observatory that's closest to you, if it's shown to have activity that's above active, so above kind of in the orangey colors at local nighttime, and there's a clear sky, you'll have a good chance of seeing the aurora. As you've probably noticed, we don't see the aurora very often in Ottawa, but you don't have to travel very far north to see it. And of course, you have to travel outside of the lights of the city. We're mostly going to see very diffuse aurora here. That's going to be very spread out and very light in color, so you really need a dark sky to see it. So the research that we do is in support of the services that we provide. So we take excuse me, measurements from satellites, measurements from the Earth, and models that we've developed and models that we've gotten from other people. We combine those to create our forecast and our services. And these are used by the Government Operations Center, infrastructure operators, and sometimes the public as well. And these are all in support of reducing impacts to critical infrastructure and technologies. So some of the services we provide, here are just some images of them, just to show you that we're looking at impacts to satellites, to communication, to power systems, pipelines, and to GPS and GNSS. So here you can see just our website. Sorry, it's just spaceweather.ca. We dropped the GC. You can still put it in, it still works. We also, of course, have a Twitter account. We're very modern. And because we're the federal government, everything's going to be offered in English and in French, whatever your preference is. So space weather influences technology and critical infrastructure on Earth and in space. And at the Canadian Space Weather Forecast Centre, we're researching this, we're monitoring it, we're analyzing it, we're providing forecasts with the hope of reducing the impact to the infrastructure and the technology that you all depend on. And of course, because you can't tell this, obviously I'm standing here quite happily, but I'm a geek at heart, so I couldn't resist. May the magnetic force be with you.
Thank you, Robin, for that wonderful presentation. All right, so up next we've got our observers reports. So if you're on the list, it'd be good if you could queue up. All right, and we've got Doug up first. You just hit,
it's a little video, just an interesting view from my balcony.
Lunar images here captured from the few days of lovely weather we had around the Astronomy Day. So this would have been the 22nd and the 23rd of April. So this first area, I've turned the image here, so north is to the left. But this is kind of the Caucasus Mountains blending into the Apennines on the right. Major crater in the upper left is Eudoxus, and some of my other favorite craters, try not to push the wrong button here. Cassini, a very interesting crater, lots of detail. And then Aristillus and Autocyclus here. Just the sun just cresting the peak of the craters. Another thing that I thought was kind of neat was the wrinkle ridges between Cernitatis and Imbrium kind of look like waves, to me anyway, of maybe the lava was flooding over the rim of the Imbrian impact crater from Cernitatis, so that was kind of cool. Moving further south, so again, this image is rotated kind of clockwise. Just some of the craters kind of in the lower part of the terminator. So I'm not sure how to pronounce it, Albectigneus is the one, big one on the left. And although this looks like Tycho, it's actually called Walter. It's a bit smaller than Tycho, but very similar in age and appearance. Moving a little bit to the east, away from the terminator. This image is in the correct orientation, so north is up. An area I always like to check out around Theophilus, one of my favorite craters, because of the really well detailed central peaks. And something I found interesting was the apron of material, molten material splashed out from the impact is actually draped over top of the central peak for the neighboring crater Cyrillus. that was really pulled out in this image. I thought that was kind of neat. Another feature that I still don't really know what the origin is, this crater chain here, which on a good clear night you can see. I'm not sure if that's an impact feature, if that's like a multiple impact from a projectile, or if it's volcanic in nature. One of my favorite features to observe when the conditions are clear enough is the hygienist rill. So that's this feature here, depicted on the 2 different nights that I imaged. On the first night, you couldn't really tell what it was you're looking at, but on the second night, you can see that actually it's a series of collapsed pits that all connect to make a single rill, which kind of gives away what the feature is. And it's, in fact, a collapsed lava tube. And some additional evidence in the area is this dark region, which doesn't seem to have a name, but scientists know that it's actually a big pile of pyroclastic material. So it's a volcanic material. So this area was at one time volcanically active, which supports this being a collapsed lava tube. This is from the second night, 23rd, so a better view of all of the Apennine Mountains in one shot, and a good view of the Hadley Rill, which I typically find very difficult because it's quite small. But yeah, it came out quite well. For those who are curious, right where the green dot is, where the Apollo 15 mission landed. So that was quite the stressful landing, I would think. Coming right in at the base of Mount Hadley. Same night, image is rotated now again, so north is to the left, looking at Rupes Recta, the straight wall, which in this image looks massive, but it's actually only 200 or 300 meters high and a couple of kilometers across, so you could easily walk up this if you had a spacesuit on. And, this crater here is Tycho, just to give you perspective. So it, some good detail of the terraces on that crater. So that was an interesting conclusion to the lunar observing. You don't normally get conditions to give images this clear in the Ottawa area, so I was quite happy. I also, for the first time, used a new camera that I bought, a ZWO ASI 183. It's a 20 megapixel camera, really tiny pixels. It's monochrome as well. So these images were all taken with an IR pass filter. So this is only infrared light that we're looking at. And the final image was before I packed up. I saw Jupiter coming up over the houses. So it was only maybe about 15 degrees up, but I figured I'll try to snap some shots of it anyway. So, may not look like it, but that bright smudge right there, that's the great red spot in infrared. So because it's warm, it appears light-colored in infrared. So that's it. Thank you.
Yeah,
that would be IO.
Next. Thank you, Jim. All right, up next we've got Gordon Dewis.
All right, so in March, when it was miserably, bitterly cold, I headed off to Jupiter, Florida, not the one that was in the previous image. And I brought with me my Ioptron SkyTracker Pro, and I was able to get a couple of nice nights, even though I was inside the urban footprint of Jupiter, which is on the east side, just north of West Palm Beach. So I was able to get one night very nice view of Orion. I believe this I shot with my 50mm lens, just tracking. It's a single frame, no stacking. And this would be my my The same camera with my Tamron SD500, 14 seconds single exposure ISO 3200 of Orion's nebula.
Okay. So this is a small galaxy cluster in the constellation Ken's Venatici, known as 6N68. It contains several NGC galaxies. They're quite small. Individually, they're each about 2 to 3 arc minutes across. So a little bit of more detail on them. NGC 353 here is an elliptical galaxy and in close proximity to NGC 5350. They're both active galaxies, but NGC 5353 is actually a blazar where its active core is projecting its energetic jet towards us. The cluster itself is located nominally 107 to 117 million light years away. The faintest object in this image that I was able to identify was this one. It's about magnitude 20.87. Let's see. Yeah, so there's quite a nice assortment of types of galaxies here. Some lenticular ellipticals and large spiral galaxies. This star is a magnitude 6.5. So, and also this one here is a kind of an irregular spiral. Pretty nice. What else? I guess, yeah, that's good. And back in March, I imaged the great Hercules cluster. Globular cluster. This field of view is approximately a degree across in my f5 1000 millimeter scope, so the full moon is about that size, my friend. And this is just the core. The full extent would fill this region. The moon was out that night, so the cluster is a pretty good target on a night like that. Galaxies don't show up very well. All right, so thank you.
Okay, Taras.
On International Astronomy Day, there was a good opportunity to see and take pictures of the moon, which many of us did, and I was not an exception. It was pretty good seeing. I was happy that the details on the moon turned out pretty well. This is obviously a picture of the moon during the daytime. That's the bluish background. Next day was even better seeing, so I took some detailed pictures of the moon surface that Jim did from his scope as well. And this is, again, exactly the same Theophilus crater with those prominent four pyramid type of looking remnants from the collision and the splattered trace on the other crater. So I think this trace here also of almost a straight line, which we both, I guess, would question who knows what it might be like, because it's surprisingly straight line here, as they left the trace perhaps of collision. The same day, again, the scene was pretty good, so I took pictures of sun with some details. Again, next day, obviously for sun it's also during the daytime, and I spent some time processing this dark spot here to get some details, so you can see the actual details in the sunspot, which are which is the umbra itself, and then penumbra, and a little bit of like granularity in the penumbra where you can see the filaments or burning material coming this way, and smaller size sunspots. As Eric just checked today as we speak on a website which shows the sun weather, this dark spot is no more, so it must have erupted, and perhaps that we can expect some materials coming towards us, or if we are on its way pretty soon. Venus, again, during the daytime, so the beauty of the daytime is that Venus is pretty high, and because it's so bright, there is some contrast which you can catch with 8-inch scopes, so that the shape of Venus is much clearer than in those pictures when it's about to set or just shortly after the rise. It's obviously in a phase which is still from crescent here. Yeah, I could push back. So, you know very much a lot about Venus. I will not be describing the details. However, the next picture is Jupiter. It's the same night when Venus was taken. So Jupiter was pretty much at pretty high elevation at that night, around 2 o'clock as well. And the prominent details which I managed to catch were a little bit of the bands. I think those are actual zones which are brighter. The bands are darker, zones are brighter. You can see a little bit of other belts on both sides. This is Io and Europa right here. So inspired by good seeing, I tried to get some close-ups, and because I stayed for more than 2 hours long, I later on combined them into comparable images with the rotation as it was seen on 2 o'clock Eastern Daylight Savings Time, then 2:30, 3 o'clock, and 3:30. Some of these pictures are not as good because seeing was changing now and then, so this particular has some ringing around, but generally I'm happy with the amount of details that I managed to catch. Thank you.
Joe Bonner.
So I took the challenge, the lunar challenge this month. Like many of the previous presenters, the weekend of astronomy day was pretty good. So I went out in the driveway to give this one a shot. So in the center there is Messier and Messier A. So Messier is 15 kilometers long and 8 kilometers wide, and Messier A is 16 kilometers by 11 kilometers. They're interesting in that I didn't get too close up with the equipment I had, but they're elongated craters. So NASA did some research and they determined that a lot of impact craters are round, but when you get to a more shallow impact angle below 45, they start to elongate. What's interesting about these two is that Messier, its ejecta is actually not in the direction of the impact. So the elongation goes in the direction of the impact. But when you get below about 5 degrees impact, you end up with the ejecta going to the sides in like a butterfly effect. This image doesn't pick it up too well, but when you look at Messier A, that's more like the angle of impact would be around somewhere between 5 and 15 degrees. And in that case, you end up with the ejector going in the direction of the impact. So that's why you can see the ejector there. And yeah, so this was taken with, I have a 8-inch Meade LX90. It's with a Hyperion 13mm eyepiece and a Canon 60 mounted on top of that eyepiece. Thank you.
Joe, up next we've got Gordon Webster.
So, I don't remember which night this was, but it was the night of the Lunar X. And I had been trying to observe, but there was too much moon. I had my 6-inch refractor. The moon came out from behind the tree, so I spotted the Lunar X and the Lunar V. And I thought, this is really good. I should get my Malin cam out and try to get some images. By the time I got it out and set up, of course, the moon had moved behind the house. And I was wondering, well, what else could I look at? And I remembered we had the challenge object. And this is what I got. This is a 20-second exposure with the Malin cam on the 6-inch refractor in Orleans. And that's a 14.2 magnitude galaxy. That was the challenge object. Thank you.
All right, Paul. Remember, 5 standard minutes.
Why did they always say that? All right, I'll be less than 5 minutes.
Standard minutes.
Trust me. All right, so I don't know about you guys, but I'm sick of winter, especially after this week where the melting snow caused flooding and I wound up with 6 inches of water in my basement. So, yeah, very delightful. So I'm jumping ahead to summer. Instead of talking about the summer triangle and stuff after it happens, I thought I'd give you a heads up because it actually is up now. If you're an early bird like me, it's rising in the east and it's up, like 3 in the morning or whatever. Anyway, there it is. Oops, where's the laser here?
It's the green button above the 2 arrows.
Oh, there we go.
The screen.
Okay, summer triangle there. Actually, I can advance there and give you a little bit of a heads up. We've got Vega, Deneb, and Altair. And so this is coming, folks. Summer's coming, and the rich part of the Milky Way is coming. So I thought I'd just concentrate on stuff that I'd actually taken last fall and I didn't have a chance to process. But I love this area. This is obviously our friend, the North American Nebula, but I was interested in this area here, which is Gamma Cygni. So this is a view just with a 16mm Bauer lens on a Canon 60D8, 24 30-second exposure stack, and you can see quite a rich amount of detail in this. This is the sort of the northern end of the Great Rift in our galaxy here, and sort of terminates right in the center of the summer triangle there. So 16mm, and then I zoom in with a 135mm Canon lens on, again with the Canon 60D8, and I wind up with that. That's Gamma Cygni is also known as Satyr, the star there. It's the bright one in the area there, and you can see this is just a very rich area of especially emission nebulas. The red that you see here, there's a variety of them here, and oops, jumped the gun. That actually worked going backwards, amazing. So you can see, again, Saturn here, and this formation here, IC 1318, that's commonly known as the Butterfly Nebula. And up at the top there, you can see NGC 6888, also known as the Crescent Nebula on this scale. So a really interesting region to look at with a small telescope, even with a good set of binoculars on a nice, clear, moonless night in the summer, which is really nice. So 135mm. This is again about 24 1-minute exposures with that particular lens. And so then I zoom in one last time on that region, and so my next shot is with a 70mm Stellar View f6 Apo. And we
zoom in a little bit tighter on Satyr there, and the top of the Butterfly Nebula. So a very rich region. Whether you're imaging or observing, highly recommend that area, right in the heart of the Summer Triangle, and it's not too far away. Did I make 5 minutes?
You did.
Thank you.
Okay, we've got, where's the observing challenge slides, Chris? Anyhow, David. Here we go.
Just give me a second to get set up here. There we go. First of all, Robin, there's a big coincidence here tonight. I too am a solar weather geek. I worked at Anderson Road in the 1980s at the Paleomagnetic Lab with John Park. And just to let you folks know that there's also a G1, a geomagnetic storm event happening the morning of the 6th local time between 2 and 5. It should give, if you're out in the country, should give a mild aurora. But with the solar cycle being the way it's been lately, auroras are fewer and far between the last little while. But also, I was also invited to work up an alert looking for Soviet subs going underneath the ice sheet back in the late 1980s as well. But still, there's another coincidence here that you need to know about. And that's when you're talking about this star called the Sun that can cause death. Death Star. May the 4th be with you. Charles, with those impact craters from, possibly a Death Star from a long time, you two need to talk to each other, maybe call, and talk about this new hypothesis. But anyways, just leaving that alone for a second. Updates on FLO. A lot has happened in the last year. The clubhouse has been painted. That's done. The observatory building painted. Cracks in the walls have been sealed. Floor has been concrete has been put in. Starmaster is in and working. Yay! With the warmer temperatures, the battery will be working at peak performance as well. An eyepiece extender was just recently purchased so that you can use longer focal length eyepieces on the Starmaster. We're talking about getting a new lawnmower, and I'll be talking with that individual a little bit later on in a couple of days. So we also need a whippersnipper. So those are some things that we're looking at long term. Repairs to be completed are as follows. We need to seal the concrete in the floor. We've noticed a little bit of a crack is developing in the same spot that a crack developed before. So we're looking at sealing that up, and hopefully that'll help prevent moisture from getting in there and cracking up the concrete a bit more. The Velcro bearing on the scope needs a little bit of care, and we're working at that once it gets a little bit warmer. And we're looking at putting on a counterweight on the scope to accommodate different eyepiece masses. So those are the things that are in the works right now. About 32 people have put their names forward to be trained on the Starmaster. I think 16 have been trained, and there's a number of people that want to go back to just to make sure that they know what they're doing. Working with the electronics seems to be the thing that's holding people up. So my suggestion for anyone here is to really read the manual over ahead of time. It's not going to make a lot of sense until you actually physically get there and push the buttons, and then it'll start making sense. But do your homework ahead of time. That's going to save you an awful lot of grief on site. So we just had a meeting with the Conservation Authority, in fact, just yesterday, and the lease is going to be renewed. So that's going to be signed off hopefully by the end of June. There was a little bit of miscommunication with regards to sending the lease last year. But Ross Ferguson from MVCA told me that that's not a problem. It was something at their end that there was just a mix-up in communication at their end. So that's going to be taken care of. Tree cutting. It just so happens that the Conservation Authority is going to be having a chainsaw safety course coming up very soon. So it looks like they're going to be having it at our site. So those trees, we're looking at taking down the trees at the southern horizon sometime hopefully within the next month or so. So that's going to be a very good thing. Funny thing is with those trees, I remember when they were planted in 1982 and thinking, oh, thank goodness they're blocking out all those lights of those houses that are just near the horizon. And then when I talked with Ross last year, we both said, what were we thinking? Oh my goodness. I mean, like 30-something years later, now so they're coming down, and they're not going to be charging us at all for that. They're very accommodating with that. The driveway to the observatory, we found out, is our responsibility. So it needs a little bit of grading to take down the hump where the grass grows, and we're going to be looking at having that done. It's not an emergency yet, but I can see within the next couple of years there's going to be some scraped bottoms and lost mufflers if we don't take care of that. So we're going to be getting a quote on grading and putting in some gravel and stuff like that. The Conservation Authority has agreed to mow our parking lot. So this is a very good thing. Last year when I went to cut the parking lot, the grass in the parking lot's about the size of this room, or maybe a little bit, about the size of this room. And I went up with a whippersnapper. My therapist says I will get over it soon. So we're all good with that. No, I actually did that 3 times with the whippersnapper, and because I wasn't going to bring up my own lawnmower. The next thing is, we have been given the go-ahead to enlarge the mound at the observatory, and there is some free fill on site. We have permission to be using the gravel pit, which is just literally beside the observatory, to get some materials from. So we'll be talking to a number of people about that. So other things that came up were, I'm just going through this very quickly. Rick and I are going to go off and mark off all the trees that need to be cut within the next week. There's going to be some future changes to the site to be announced. We have to decide that with council, some projects that we've got possibly on the go. And the latrine at the site's also going to be redone. We're going to be putting in a 45-gallon plastic drum and use that as a collection thing for so we can have it pumped out. So those are the updates that we have so far. And are there any questions at this point?
Yes. David, what about a mosquito zapper?
Well, speaking of vermin, there's a number of things there. The thermocells that people, hunters and people like that use, the problem with that is that they work great when there's no wind. Unfortunately, there's usually a wind, so that's not going to work. There is another problem, and I need to tell everyone well ahead of time. We have some unwelcome guests at the observatory of the striped variety, and just so happens that you now know a licensed trapper. However, if this is a female and she's set up shop with her kits, I will not be trapping anything until late summer, early fall, just out of ethical concerns, because they're important too. And so we're going to be trying to work that out. We have permission from the Conservation Authority to deal with them, and I'm going to try to deal with them in the most humane way possible. So when you're out, make lots of noise. Don't leave the clubhouse door open. And they will, honestly, they'll just leave you alone. That shouldn't be a problem. Okay? So the mosquitoes, not much I can do about that. The skunk, just have to tolerate them for the next little while. And you respect them, they will respect you. That's all there is to it. Anything else? Going once, twice, thrice? So, thank you very much.
Did you run away with the remote? Oh no, I have it. There it is. Okay, so we've got some dates set out for the FLO Star Parties. The first one being May the 12th. Is that a Saturday?
Yeah, Saturday.
Next Saturday. So that's the first FLO Star Party, members only. And you'll see the other dates there. You can visit, so we've also got our public star party schedule set out. Public star parties happen in the parking lot of the Carp branch of the Ottawa Public Library, so that's at the defense bunker. You can see it right there. Oh. So these are the dates. Our next public star party will be on Friday, May 11th, with rain dates of May 12th, May 18th, and 19th. Yes, in Astronauts, the date of the first members only star party had been listed as May 18th. It is in fact the 12th. Alright, the observing challenges. So as always, take note of the challenge objects, make sacrifices to your deity of choice asking for clear skies, make observations and record them, images, sketches, notes, they're all welcome during the observation reports, and submit them for the observation reports and for Astronauts. Your director is Gordon Webster, so send it to him. The first challenge, which is our beginner challenge, is M3. It's a globular cluster in Canis Venatici. And even though its home constellation is one of the sky's dimmest, M3 is one of the sky's brightest globulars at a magnitude 6.3. It's visible naked eye as a faint smudge under dark skies. To find it, imagine a line starting at Arcturus, running about 25 degrees northwest to Carcaroli, and M3 lies just about halfway, 12 degrees from Arcturus. Okay, our intermediate challenge is the antennae galaxy pair. The antennae are a pair of galaxies in a celestial deathmatch of tug-of-war, each being yanked apart by the gravity of the other, resulting in churning complex mix of red hydrogen 2 stellar nurseries and blue clouds of newly energized stars. At first glance, all you may see is a single 10th magnitude glow, but under higher magnifications, it'll reveal a hook-shaped image with a faint extension coming off towards the south. So that one is right there. So that one is it's in the constellation Corvus. All right, and our advanced challenge, it's another tricky planetary nebula. Well, its location is pretty easy to find. It's just 1.6 degrees from Iota Hydrae in the constellation Hydra. The object is right next to a 7th magnitude star. And in fact, the nebula's gaseous shell extends almost to 5 arc seconds, and it overlaps part of the star. So it's tricky to see just because of the contrast. So you'll have to get creative there. So it's 13.4 magnitude, and it's another one of these PK objects, PK 230 plus 34.1. And here's our lunar challenge for the month. O'Neill's Bridge is oddly not actually a lunar feature. It's an illusion created by the light of the sun and the resulting shadows when the sun lights the area from a particular angle. So it's right there. Yeah, basically in 1953, John O'Neill, who was a science editor for the New York Herald, he turned his 4-inch refractor at the moon and began surveying Mare Crisium's western rim at 90 times magnification. And then as he increased the magnification, he ended up seeing what looked like a gigantic natural bridge arcing over the gap between Promonerum Malivium and Promonerum Lavinium. Anyway, he cooked up a big storm about it, and it was actually confirmed by various other sources until later it was recognized as just an illusion. So in order to spot this, you need to observe it on either the 16th or 17th lunar days, when the sun is at a particular angle. All right. Our public outreach program is looking for volunteers. They were out helping a group of Girl Guides recently, but need a few more people. You can reach out to Latif or Dano. These two email addresses if you want to volunteer for public outreach. No book of the month this month, since Estelle's not here, which also means the library is closed. So those of you that have books out, you can keep them another month. Here are the folks that help run the club. Our website, you can find recordings of our center meetings if you ever miss one. And we had an audience of about 98. Thank you to all our speakers. Thank you, Dr. Robin Fiore. Thank you, Chuck O'Dale, and thank you to everybody else. And thanks to the museum for hosting us. Our post-meeting meeting will be at Grace O'Malley's. That's just on Ogilvy Road, just off the Aviation Parkway. Our June meeting is June 1st. We'll have Simon Hanmer giving us a very interesting talk on rapidly evolving solar system science. Yes, and we'll have the swap table before the meeting. Chris, approximately what time will we have that?
Half an hour before.
So starting at 7 o'clock, the swap table, bring any gear that you want to sell, bring your wallets full of money, get some new toys, but not too many, because otherwise we'll get nothing but cloudy skies. Here are the benefits of membership. You'll get access to the Ted Bean Loan Library, where you can borrow equipment. You'll have access to the FLO, which is our observatory, our book library, the various publications put out by the Society. And now it's time for door prizes.